So our next topic in this lesson on time series analysis is that of wavelets. So here we have a time varying signal, and we can see that it consists of initially a low frequency oscillation that halfway through switches to a high frequency oscillation. Now with Fourier analysis we can only pick up the frequencies of the oscillations that are in the signal, but we don't get any information about what's happening at different parts of the signal. So we just get an overview. There are these frequencies present. And if we want to pick up this fact that there's a change in the frequency of the oscillation and therefore a change in the behavior of the system halfway through, then that's when we go to wavelet analysis, which will tell us about the frequencies not just overall but at particular parts of the signal. And I'm going to describe the principle behind wavelet analysis, but again it's not something that you would actually do manually. You would get a piece of software that is capable of wavelet analysis, and you would feed your data points to it and allow it to do the number crunching and just give you the results. But the mental picture behind what's going on with wavelet analysis is that we have a wavelet, so it's something like this. And we slide this wavelet up and down along our signal to see how well it matches. So we're moving this back and forth along here. So at this point, this part of the wave, a part of the signal, it would match quite well. The frequency of the wavelet is the same as the frequency of the signal, whereas here it wouldn't match. So as we slide this wavelet up and down, we'll get a series of numbers showing the strength of the match between the wavelet and the signal at that point. And so we'll get numbers for all the way along here. And then what we do is we then repeat this process, but now with a wavelet of half the size. And so we now slide this higher frequency wavelet up and down and see how well that matches. And then an even higher frequency wavelet up and down. So we've got different frequencies of wavelets, and we've for each one we've got a series of numbers showing how well it matches along at each point along the signal. And there are many different shapes that you can choose for your wavelet, and you know, some people prefer one rather than the other, so they'll say, you know, you get better results with this or with that. So there is to some extent a bit of an art to you know, how you do your wavelet analysis, what type of wavelet you use. And I'm now going to show you the kind of output we can get from a wavelet analysis and how to interpret it. Okay, so here are 4 different signals with different waves, and we study them with what is known as a scalogram, which is what's shown over here. So a scalogram is a plot of frequency against time, so it shows the frequencies present in the signal as a function of time. So if we start with this first one here, well, it's just one single sine wave with a very definite frequency, a particular frequency. So that's shown over here, that there's just one frequency over the whole time of the signal. Now with the scalogram, we're plotting frequency against time. So we don't have, you know, we need a third dimension to show the power in the frequency at that that particular time. So you know, when we had for an ordinary power spectrum, we were showing frequency and the power in the spectrum up there, and so we're looking at a particular frequency and seeing how much power is in that, you know, how strong a signal at that frequency is in the data. Well, in this case we're plotting frequency against time. So to show the strength of the signal at that frequency and that time, we need this third dimension. What we do is show it by the density of how this is coloured in. So there will be some kind of shading, you know, and you can choose different colour schemes. But here I've got showing it in red, and the deeper the red, the stronger the signal at that particular frequency and time. So in this case, with just one frequency in our signal, we just get a strong solid band all the way through for the whole time period. Then in our next example, we've got a signal that is low frequency at first and then changes to a higher frequency halfway through. So for that, we'll get a scalogram like this. There'll be initially just one frequency, the low frequency, and then halfway through it switches to the high frequency signal. Then this one is a superposition of these two frequencies, the lower frequency and the higher frequency. So when they're added together, you get a waveform that looks like that. So this is a mixture of the two, or the whole way through. Both are present, the low frequency one and the high frequency one, superimposed on each other. So what we'll get is a band for each of those two frequencies, the low frequency and the high frequency, and they'll be a little bit less shaded because now the power is shared between the two frequencies. So there's some signal strength at that frequency and some at that frequency. So I've tried to show those as a bit, you know, lighter shade. And then for our last one, we've got initially just a pure signal, pure oscillation, then the superposition of the two frequencies, and then finish off with the high frequency oscillation. And that results in a scalogram like this. So we've got the low frequency at first, then a period of overlap of the frequencies where both of them are kind of sharing the power, and then that one peters out and we switch to just the high frequency. So wavelet analysis, the best way to picture your results is with this idea of a scalogram, and this is how to interpret it. And now we'll look at a practical example where we'll look at the scalogram we get for the data I looked at in the discussion of Fourier analysis about the oscillations in disturbances in the Roman Empire, or in ancient Rome. Okay, so just to recall then, we had data on the distribution of disturbances in Rome between 600 BC and AD 600, and just presenting it in a stylized way, it looked something like this, that there were regular oscillations up and down, and also on a longer time scale there were periods when the disturbances generally were larger than at others. And we looked at doing a Fourier analysis of that, and we get the power spectrum, P power for spectrum, when we're looking at the different frequencies. And we found that there was a peak here at a period. This is frequency per century. This peak represented oscillation with a period of about 340 years. So that's the big oscillation here. And then there was another peak to represent, or that showed there was a signal with a frequency of about 2 per century, which corresponds to a period of 50 years. And that's these shorter oscillations, or higher frequency oscillations. Well, if we do, we can take the same data and this time do a wavelet analysis of it and get a spectrogram. So now, instead of just looking at what frequencies are present, we can look at what frequencies are present against the time. That's supposed to say 600 at the end there. That's the time axis. And if we do that, what we find, and this is just stylized. I mean, it's just to, again, to present the principle, but it's a reasonable representation of what you actually find. So we get this fairly strong signal here, the 340-year oscillation, the low frequency oscillation, with a period of about 0.3 per century. That's down here. And then we also find up here there is indeed this 50-year oscillation, but in this case what we find is that it kind of becomes weak at certain points. So it was relatively strong in the early days of Rome, but then it kind of disappeared, and then it was very strong during the Roman Republic, which was, a period of time of a lot of political struggles and disturbances. And so it seems that generational cycle seemed to operate very strongly during the Republic. Then it kind of started to peter out during the early Empire, and during the 1st and 2nd century it kind of disappeared. Maybe this was, we could interpret this, maybe this was a time when Rome's attentions were elsewhere, or maybe it was just generally peaceful, or because people were, it was a time that people felt more prosperous or something. We could start to investigate why we think that is. But anyway, this intergenerational cycle seems to have petered out, but then it came back again later on from about the 3rd century onwards. Then we also find some other cycles present in the data, so that at certain points, particularly around here, when this generational cycle was petering out, there was a cycle, I haven't really drawn it very well, but a cycle appearing for a while around about here that's about 1 per century. So that, it didn't necessarily come out in the Fourier analysis, but it seems to come out in the Wavelet analysis, that there was a period when there was a 1 century oscillation. So that because it only lasted a short time, it doesn't really come out in the Fourier analysis. But with a wavelet analysis, we're more sensitive, and we can pick up that there was kind of a shift in behavior of the system. So you can see that the wavelet analysis can maybe give us more information and propose more questions, interesting questions for us to try and drill down and try and understand the detailed structure of the frequency, the cycles in disturbances against the whole time, which is, there over 1,000 years of Roman history.